Thanks everyone for joining us today for this session. My name is Noam. I'm with PlaxidityX and very excited to co-present this session with Christopher from Marquardt. The plan for this session is to start with a quick introduction to automotive cybersecurity, regulation, and DevSecOps. And in the second part, Christopher will take us through the Marquardt journey to DevSecOps. So just before we dive in, for the benefit of those of you who are not familiar with either PlaxidityX or Marquardt, we'll have a very brief introduction, and I'm going to start with PlaxidityX. So if you are not familiar with PlaxidityX or with our name, most likely it is because we just very recently rebranded as PlaxidityX. You may, however, be familiar with our previous name, which was Argus Cybersecurity. So we have been around for over 10 years. We are all about automotive cybersecurity. This is all we do. We have global presence in the major automotive hubs. We invest a lot in research in our domain, invest in technology and intellectual property, patents, and the like. We offer an end-to-end solution starting from DevSecOps, which is obviously the topic of today's session, through in-vehicle embedded intrusion detection and prevention systems, and through XDR platform, which you typically use in a VSOC, a Vehicle Security Operations Center, to track the entire fleet of vehicles. So Chris, would you like to say a few words about Marquardt?
Yes, with pleasure. First of all, also thank you from my side for attending this webinar. And let me tell you some key facts about Marquardt. So Marquardt is a global tier 1 with around 10,000 employees worldwide, spread over 21 locations in 13 countries and over 4 continents. And we have around 100 patents and industrial property rights. We develop ECUs up to Cybersecurity Assurance Level 4 and up to Automotive Safety Integrity Level D. Within this context, we develop and produce operating components like steering wheel switches, climate controls, and other HMI components, drive authorization system like digital key or car key solutions, parts for e-mobility like charging systems or battery management systems, as well as components for fuel cell stacks, like a cell voltage monitoring, and also for the non-automotive area, a variety of switches, sensors, and other systems. And with this little overview, back to Noam.
Thank you, Chris. So let's get started. So I want to start by referencing a recent survey. And this is a survey of automotive manufacturers. The question that we're looking at right now was, what are your top external obstacles for automotive manufacturing? And we can see the 2024 results. Cybersecurity risks are #1. So this is very interesting also, because if you look at the trend, the same survey has been going on for several years. And cybersecurity risks were mentioned before, but even if you compare it to the previous year, 2023, it's not even in the top 5. The cybersecurity was #9. A year ago, it jumped to #1. So this is a pretty dramatic increase in the focus on cybersecurity and realizing that this is a major obstacle. And if we're trying to think what are the reasons that we have this somewhat dramatic kind of increase in focus on cybersecurity risks, one would be the kind of the obvious increase in chatter, increase in threats and risks and actual vulnerabilities discovered in actual vehicles on the road. The increase is almost exponential if you compare it year over year in the last few years. Many of those vulnerabilities are reported by white hat researchers, but not all of them. Some of them are actual attacks. So that's kind of the obvious aspect. Another one, or another reason why cybersecurity risk would jump to #1 by automotive manufacturers in 2024 is the regulation, and a very specific regulatory milestone that we just recently had. So that is a great segue to talk a little bit about automotive cybersecurity regulation. Now, if you are joining us from anywhere from Europe or from Japan or Korea, most chances are you are familiar with the UNR 155. This is the most well-known, the most mature automotive cybersecurity regulation, applies in all of the European countries, as well as additional member states of the UNECE body, such as Japan, such as Korea. And this is already in effect. So this was put in motion a few years back, and there were two milestones. One of them was 2 years ago in 2022, when it was applied to only for new vehicle types. But previous vehicle types that were approved before were kind of still exempt. And this exemption was over in the second milestone that took place back in July, not too long ago. So starting July 1st, all those countries that are subject to UNR 155, every a new vehicle that is registered and put on the road has to comply with the regulation. So that's a major milestone, and might explain, at least in part, the result of the survey we saw in the previous slide. Just a few words. Beyond UNR 155, there are similar type of regulations that are in the works for additional regions and countries. Next in line in terms of timing is probably the Chinese regulation, the GBGBT. It's gonna apply slightly after the UNR in terms of timeframes, but I believe the first milestone is gonna come up in 2025, and then there are additional milestones after that. Another country that is a little behind in terms of timeframe, but already announced and working on the regulation, or their version of the local regulation, is India. So we can see that more and more countries and regions are adopting local variations of this regulation. Now, even in countries where there is still no formal regulation, including important regions like North America, we still have industry standards. The most well-known is the one we see here on the top left, the ISO 21434. That's an international standard. As a standard, it's not mandatory on its own, right? It's a voluntary, it's like a state-of-the-art document. Having said that, sometimes this standard or similar standards are being referenced by actual regulations. So by association, they become part of the regulation, and then they are mandatory, which is the case, again, with 21434. We also have in local regions and countries, sometimes best practices guides. The example here is from NHTSA, the National Highway Traffic Safety Administration in the States, and they publish a cybersecurity best practices for the safety of modern vehicles. So again, not a mandatory regulation. It's more a voluntary kind of best practices document, but at the same time, not something that anyone wants to ignore. And maybe last comment about the regulation, the automotive cybersecurity regulation is not just a formality. It's not just some legal process or paperwork you have to do. It has real life business implications on automotive manufacturers. And we have here, hopefully you can see a couple of examples, kind of news clips about well-known brands that decided to discontinue certain models, sometimes very popular models, just because those modules were designed a few years back and they are just too far from meeting the cybersecurity regulations. It's just going to be too complex or too costly to retrofit them, and they will eventually be replaced by newer models. But think about discontinuing a very popular model. It has financial implications, maybe reputational implications, and so forth. So the regulation is something very, very important that can have real implications. Okay, so I think we all agree about the importance of automotive cybersecurity and understand the regulations that we are facing. So how do we get there? How do we make sure that the products that we're putting out there, whether it's components or actual vehicles, have the best level, the highest level of cybersecurity, the best cybersecurity posture? And here I want to briefly talk about the concept called shift left or shift left security. What you see here on this slide is coming from a research about software development, not automotive specific, by the way, software in general, and about what would be the cost to repair a certain software defect as a function of where in the process you are doing it. So comparing it, the two extremes, right? The extreme on the left, which is when you are just starting to write the code, versus the other extreme, where the product is pretty much ready to be released. And the difference in the cost is staggering. As you can see here, it's going to be 640 times more expensive to fix that defect at the end versus fixing it at the beginning, right? And then obviously there is some kind of a continuum there. So the more you are moving, you are discovering, identifying, and addressing that defect, the earlier you are doing it, or the more it is to the left in terms of if you think about the project timeline, the cheaper it will be for you. That's talking about cost, but you can also imagine that the time or the time to market impact or the potential delays are going to be part of it as well. So if we look at the V model, right? The system development life cycle that is very common in automotive manufacturing. And what we see here is a slightly simplified version. Usually we have more steps of design and more steps of testing and so forth. But just to slightly simplify it, let's think about four main phases. Starting with design, right? We are designing the product. Now, when we are thinking about the security context, we also need to make sure that we are looking at the security aspects of the design. Then we have the implementation. In the case of automotive software, implementation is mostly about writing the software, writing the code. The next phase is the testing and integration. And here we are talking about integrating third-party components, right? It can be coming from our supply chain. Maybe we're building a vehicle and then we are putting ECUs inside. The ECUs are coming from down our supply chain. We need to make sure that everything is okay also down our supply chain. And a quick reference to the regulation, the OEMs are responsible from a regulatory standpoint to make sure that everything is okay at their supply chain. So it's not the fact that the problem came from another supplier, not a good excuse. The OEM is still responsible for that. So that is the testing and integration phase. And then we have the operation. So in our context, think about let's say we finish the vehicle and we produce the vehicle and put it on the road. You might think of it as kind of the end of the journey, but from many aspects, it's really the beginning of the journey, because that vehicle is going to be on the road for many years, right? 12 years on average, life of a vehicle on the road, could be a lot more. And you still need to make sure the cybersecurity posture of the vehicle is fine. And if you think about it, even if the vehicle was completely free of known vulnerabilities the day you put it on the road, that can change. So tomorrow and next year and so forth, new vulnerabilities can be discovered. They were already there, right? Originally in the vehicle, it wasn't public yet. It wasn't known yet. Once we know that we have a new vulnerability that we are aware of, we have the responsibility to take care of it. And if it's important, high priority, we have to deal with it, even when the vehicle is now on the road and it's going to be there for many years. So that's the operation part. Okay, so let's think about the traditional approach to addressing all the security aspects, right? So starting with the TARA, threat assessment, risk analysis, right? It's a very manual process, right? Traditionally, we have the system architect or the system analyst, maybe it's a team, and they need to take the system design, whether it's the component or the vehicle, and look at assets, identify the assets and identify the threats and the damage scenarios and the attack path, and do a risk assessment and eventually come up with a cybersecurity concept, how to handle this product, right? That's the first part. And it's all being done manually, right? The second part is we are writing the code, writing the software. We need to apply and put in security measures and features in place. maybe do code review, and this is a very, very manual process. And eventually, we have a product in place, and we need to scan for vulnerabilities. And for that, we need to get to the SBOM, the software bill of materials somehow. Maybe we have it. Maybe it's a little harder to get because it's something that came from a supplier, and maybe it's just in a binary form. We don't even have the code for it, and so forth. So this is the kind of the traditional approach. So what would be the main challenges if you think about this process? And we have them listed in the next slide. So again, thinking about those three main steps, starting with the design, right? We have a manual process to create the Tara. First of all, it requires us to have domain expertise, right? Someone or a team that understands both cybersecurity and understand the automotive and the vehicle design. There need to be a sync between the architecture and the Tara. What I mean by that is that it's convenient to think of it as a linear process, right? We do the design, we finish it, we do the Tara, we finish it, we move on. That's nice, but in real life, it's not always as simple. So in real life, we have iterations. Maybe after the Tara was created, we need to go back to the design and make some adjustments because we discovered that some things needs to be optimized, and we make changes to the architecture. Now we need to also go back and revisit the Tara. Potentially, we need to make changes to the Tara. Do we always remember to do it? Do we always know that the Tara is synced with recent changes? It's not an easy answer, managing all those platforms. So this is in the design phase. Then we have the implementation phase. So we are writing the code. We are basing it maybe based on the Tara, but even to scan for vulnerabilities while we are writing the code, how do we get the SBOM, the software bill of material for our code? We're still writing the code. We're using all kinds of libraries, maybe open source, maybe other types. How can we create that SBOM, and then how can we scan it? Are we even doing it as part of our development or not? So all of these are kind of challenges or potential gaps. And then if the Tara that we created in the previous step, if it's not the most optimized or updated Tara, because of the reasons I mentioned before, then maybe the security measures that we're putting in place are not optimized as well. Maybe we are missing out on some weaknesses or some risks, and we have a problem. So that's the implementation phase. And then the next phase, we are getting close to the finish line. The product is getting close to be ready. We want to do some additional testing. We have, as we mentioned, we have binaries coming from ECUs, from suppliers. Do we have SBOM for those binaries? Can we scan for that automatically? Again, not always easy. And maybe another aspect of it, when we do find a vulnerability, and let's say that this is a public vulnerability and it's a very critical vulnerability in a certain package of software, do we have the context for it? And what I mean by that is that without a context, all we know it's a vulnerability and it's critical, and maybe we have to stop everything and address it right now. But if we had the context, right? If we had the context coming from the Tara, we could see that maybe in one use case or one scenario, this vulnerability is in our ADAS system. So clearly very critical. And then think about another scenario. The exact same vulnerability is in an ECU that is responsible for something minor like the ambient lighting in the vehicle, right? Probably slightly less critical than the ADAS system. So now we can adjust and using this context, make sure that we prioritize correctly. But if we don't have that link, if we don't add that context from the Tara, then we don't have the ability to do that. So this introduction was really in order to suggest a new approach. And obviously, from the title of this session, you can guess that this approach is called DevSecOps, right? So DevSecOps, it's if you know the concept of DevOps coming from software development in general, right? Development and operations, all those processes, all this automation that is in place to facilitate the development process. DevSecOps is DevOps and then we add the security to it. So now all the security operations are also part of the development process. And think about all the different steps that we briefly discussed in the last few minutes, right? Starting from the design. And what you see here is the PlaxidityX DevSecOps platform. If you look at the top, starting with what we call the Security Auto Designer, which is an automated way. It's a product that automatically reads the design documents of the product in an ECU or entire vehicle, and automatically creating the TARA for you, right? Using a database of threats, which is dynamically updated all the time with new threats. Now you have an automatic TARA. So not only you save time, but you can have that TARA integrated into other aspects here. So we have the code security, right? Creating the SBOM for your code. Every time you commit a new piece of code, you have a new source code, or you changed it, automatically an SBOM will be created and vulnerability scanning will take place. And what do you know? If we found some vulnerability, a ticket will automatically be opened for the relevant team to handle that. This is during the coding, writing of the software. And then once the product is more mature, we want to test it when we integrate with the supply chain. Then we have the supply chain security component, right? So again, scanning for vulnerabilities. But now when we are creating the SBOM, sometimes we need to automatically extract it from binaries. And then maybe we want to do fuzz testing to the actual end results. The product is almost ready, just to make sure there aren't any other zero-day vulnerabilities that can be found. Think about it as not just as a set of tools or products. It's that as well, of course, but think about the benefit that you can get by the engagement, the interactions between them. And maybe again, I'll go back to this example that I mentioned before. If right now the auto designer, right, that analyzed and created the TARA can provide this context and say, hey, this component is in charge of the autonomous driving versus that component who is in charge of the lighting or the windows, maybe less critical. And the vulnerability prioritization engine, when you are scanning for vulnerabilities and looking for the next best action, what is the action plan, right? I have 1,000 vulnerabilities, but a lot of them are irrelevant or low priority. How do I handle it in the most effective way? Can leverage that context in order to give you the best optimized action plan. Okay, so just a quick summary. We very briefly introduced DevSecOps. We're going to see a little more into it shortly when Chris will discuss the Marquardt use case. But really, in a nutshell, right, the main benefit of the DevSecOps approach is a better product cybersecurity posture, right? The level of cybersecurity of your product when it's ready is going to be better. But this is not the only benefit. Think about the time to market, right? If your product comes to close to the finish line, and it has a lot of issues that you discover last minute that you need to handle, versus discovering a lot less issues, or maybe not at all, because we already addressed them earlier in the design and then in the implementation phases, then you are avoiding unnecessary delays. So time to market is another benefit. And of course, almost goes without saying, but there is the regulation. So compliance with the regulation, and the regulation is specifically addressing those requirements, the TARA, doing fuzz testing, doing vulnerability scanning, and so forth. So having that approach built into your software development process is going to help a lot in your regulatory compliance activity. So with that, I think let's switch to the second part of the session, and Chris will take us through the Marquardt journey. Chris.
Yeah, thank you, Noam. Thank you for giving us a specific view on security in the development lifecycle, and especially showing us the challenges we are facing. Let me introduce you now to our case study, how we at Marquardt implemented security into our development lifecycle, and especially going for shifting left for security. First of all, the reason for going this way is the the combination of the immense cost for fixing defects as Noam described in its presentation, like 640 times as when first developed, as well as the liability claims our customer can come up with when our products are in the field. This would cost a lot of financial risk, and it would bring us a lot of reputation loss, which can lead to fewer sales, and therefore is a risk for the whole company. So the origin of our thoughts was, as already mentioned, the DevSecOps approach, where you can see the infinite loop here, which emphasizes the collaboration between the software developers on the left side, the IT operations team on the right side, and the security team, which is all around and hopefully all inside. Where the software developers normally develop applications or functionalities, the operations team runs, configures, and administrates IT environment, and the security team ensures, on the one side, a proper security concept within the development of applications and functionalities, and on the other side, IT operational environment hardening and the integration of intrusion detection, prevention, or reaction systems. When we try to transform this approach to the automotive area, we first thought of the following points of the operations part. Typically, the vehicle manufacturer is the one who deploys the vehicle in a verified and validated state. He has the advantage of operate the vehicle and to integrate the mentioned systems like IDS, IPS, IRS, and he can also perform forensic analysis and so on. This is what N-tier structures, like we as a tier 1, cannot. We cannot monitor the vehicle network. We cannot analyze the ECU's operational state. We cannot detect intrusion events or suspicious behavior of ECUs, and so on. But what we as part of the supply chain have are the PSIRT interfaces. PSIRT is the abbreviation for Product Security Incident Response Team. And these interfaces go through the whole supply chain, and we are interconnected with each other, and therefore can exchange information. And we have the knowledge about the ECU's internal structure. When we now take a deeper look on the first part, the operate part, I've mentioned the PSIRT interfaces. We see that we are connected to vehicle manufacturers, which can send vulnerability or threat information to us. We can receive vulnerability or threat information from our subcontractors. We can receive them from hardware vendors or even from third-party component providers and tool providers. Just to mention, AUTOSAR standard software is a big topic, and also compilers, which have a big influence on the created software binary. We put all this information received via PSIRT into a database and go to the second activity in this loop, the monitoring of our digital twin data. What's a digital twin? A digital twin is a representation of an ECU, in this case, in the digital world. By simplifying that is to say we list all of the components of the software and of the hardware to define the ECU in a digital world, and then we are able to scan public or private vulnerability databases for a match. Probably not, but we are able to scan. We at Marquardt are integrating the software supply chain security tool from PlaxidityX to implement the vulnerability and threat information, which refers to specific components, for hardware components, for software components, and use this information within our process, but I will refer to this in a later stage. When we now go from the operate and monitor to the development part, we start with the plan. As Noah mentioned, we have to go for analyzing our risks. We have to create a TARA, the threat analysis and risk assessment, and therefore we are going to iteratively modeling our threats with the help of a threat database. This threat database is divided into functional clusters, like for drive authorization ECUs, cell voltage monitoring, and just to bring one example. A typical attack scenario on a drive authorization ECU, like when a thief wants to steal your car, is the so-called relay attack. When the attackers come with two boxes, which are interconnected with radio frequency, and they just simply extend the signals which are exchanged between your key and the car. And the key can lay in your home. They can open the car, start your engine, and drive away. This attack should be part of every TARA for drive authorization ECUs. That's why it is so important to have this database and to not start from scratch for every ECU. Additionally, we go for the vulnerability analysis as in the initial phase, where we scan all our available catalogs, like one from the UNECE regulation 155, where typical weaknesses or vulnerability catalog is mentioned for system specifications, where you can check if you thought of everything. This is also done for hardware and mechanics and software. And at this point, we also learn from the incidents out of the operate and monitor. We use our database to manually, in this case, transform these information, because we don't have the ability to analyze the context automatically. We analyze it and put the corresponding threads also into our TARA database. So, for example, if these boxes I mentioned for the relay attack are getting cheaper, are available on eBay now, then the equipment is publicly available, and this would also bring the attack feasibility within the TARA to another rating. So there's a higher risk because the equipment is publicly available, and you have to recalculate also your residual risk. So perhaps you have to use a stronger security control to protect your assets from this attack. Out of the TARA, we create cybersecurity concepts, and there also we have generic ones that nobody starts from scratch, which also contain a proprietary CBOM. So the cryptographic bill of materials is in there, where we are able to see which cryptographic algorithm is used in this ECU. And when we think of quantum computers, maybe in the future, there would be algorithms which are not secure anymore. And with this CBOM, we are able to define which algorithms have to be exchanged. And the created cybersecurity concepts can then be tailored down corresponding to the cybersecurity assurance level, because not every not so critical ECU needs the same amount of security as high critical ECUs. Now, after defining which security implementations shall be done, we have to implement them. And that's why we doing this in the activity code here in our infinite loop. We support our developers by integrating security plugins in their IDE. So when they write their first line of code, or even some lines of code, and they are implementing a weakness in the source code, they would get a direct feedback and must change this code to be not lead to a vulnerability at the end. We also support the coding by test-driven development and also by pre-commit hooks. So if a developer wants to commit his changes into a version management system, he must run different tests to be able to provide and commit the changes to the mainstream. Also, we integrate secure coding guidelines, which are also dependent on the cybersecurity assurance level. So for high critical ECUs, we go also for defensive implementation techniques. For example, if the ECU could be prone against side channel attacks, then you have to also go for these defensive implementation techniques. And an important topic on this page, which is not directly only important for developers or for only coding, it's a general mindset, it's a cybersecurity mindset in your organization, which we provide or which we support by provide trainings. and the presence of the cybersecurity engineers or the cybersecurity team in the development or the operations team to not pre-provide this. And please do me a favor to emphasize this a little bit. Ask one of your developers if cryptographic keys can be found in unencrypted memory areas. I would be very interested what the answer would be. A short hint on that: yes, it is possible. And in actual environments of embedded developers where you don't have enough memory and you have limited processor power and so on, sometimes developers need ways to fix problems, and they should be aware of the problems such topic brings for cybersecurity, and they must be aware of the risks behind. When it comes to building the software, because we implemented all of our security implementations, we are going for the software composition analysis. On the one hand, you can create the mentioned software bill of materials, so the list of software components on your own by a simple script, which is used within the build chain, or you can use tools, I will come up later, to extract this information from the binaries. This is especially useful when you want to keep track of cybersecurity supplier quality assurance, so that your suppliers, like providing one single software component, cannot perform a vulnerability scan. Then you can do this for them to be sure that this component isn't a vulnerability for your whole system. Yeah. At this point, we integrate the information and use the tool from PlaxidityX, the software supply chain security, to integrate the vulnerability scanning in our CI/CD. Yeah, CI/CD, the continuous integration and continuous delivery, is a real cornerstone of DevSecOps. And without it, I think the approach wouldn't bring so much. So we use this for sure, and we integrate these security vulnerability scans there, and you can see it via these different process steps. And at the end, or in the middle end, quality gate in a yellow box, where you can define that software build with security vulnerabilities wouldn't go to the next process step. And we have to first fix these vulnerabilities, and then we can start from scratch and do the scans again. And only if it's vulnerability free, we can continue. And this is done for every new software build. So you have this continuous feedback to the developers that they are secure. Yeah, now that we implemented everything and built our software, the next important part is on the row. We have to test this. And if we look at the DevSecOps approach, we find many buzzwords which are already familiar with us, but we have to connect the dots a little bit. So if we talk of static application security testing, we already do this by static code analysis with MISRA metrics, HIS metrics, C or CWE scans. We have the dynamic application security testing by functional security tests with regression testing, and also the more interesting part, the interactive application security testing. So where you want to know which lines of code your stimulation via some test script goes. There you can analyze the code coverage. We already have different quality aspects for code coverage, like for statement or branch coverage, which should be at 100% in automotive development. But for functional safety critical system, we can also go for MCDC, the multiple condition decision coverage, which is a very high code coverage. And this also gets into we take into account when we talk about critical ECU, so critical also with cybersecurity risks. When it comes to model-based development, we use Stimulus model-based checking tools and perform integration tests, as well as fuzzing. And for sure, there's a penetration test normally at the end, because the test method behind penetration test is the experience-based test. But for sure, you can also integrate tests in your automated tests where you just scan all your diagnostic ports. The one which are not accessible are really closed. But yeah, it's discussable if this is really a penetration test. Yeah, and the overall high automation level is needed for having this continuous DevSecOps approach, also with testing. Yeah, now that we verified all of our implementations and validated the risks from our Tara with the corresponding security controls, we are ready to release the ECU or the product to our customers. And regarding the ISO 21434, with the release to the field, the post-development phase starts, and we support our customers with our cybersecurity service called Digital Shield, where we don't let the infinite loop break here. It will continue by providing operation and monitor for the whole the product life cycle up to the end of cybersecurity support, and also have the ability to have a development team ready. When it comes to a vulnerability, our customers are able to react because we have everything in place. As the DevSecOps infinite loop would now continue from the beginning, I want to summarize my thoughts a little bit by giving you some tips if you want to implement DevSecOps in your organization, where first of all, as I mentioned, the cybersecurity mindset and the awareness is important. You have to get the support from the upper management. There are a lot of things to do to get cybersecurity into the minds of everyone, which is part of the development lifecycle. You have to invest there and therefore get support from your upper management. Then, as the collaborative part of DevSecOps already says us, be inside, communicate. Don't think within islands. Let your security team don't be the ones who create security requirements and then have never been seen. They have to be part of the teams. They have to discuss the problems the teams are facing with security implementations together with them, and shouldn't be outside. And for sure, what you can automate, please automate it. It's nothing more frustrating than creating a Tara the fourth or fifth time from scratch. You should use databases for it. You should automate all the repeated stuff, your engineers, which should focus on getting better in their Tara quality, on introducing more attack vectors and so on. They should be supported by automations. And with these tips, I will close my presentation. Thank you.
Thank you very much.